I also didn't realize that most of the slides were on the website. Yeah, they were the ones that made it.
Sure. Yeah. Hi, everyone. If you've seen me running hectically around, my name's Supriya. I'm the head of comms and sponsors. I think I just took my earring out like a pirate, so you know what? That's not the worst thing to happen today, so it's fine. Yeah, so I'm Supriya, head of comms, sponsors. It's really great to see all of you. Thank you so much for your resiliency and support through this crazy process as we kind of navigate in the power. I assume it's the first of the DMV cons, so several cons at first. I guess that first time to us. So again, super appreciate it. I just want to communicate a few things. I've been sending frantic emails so you might recognize my name, but just in case. Oh, is this not working? Oh, I'm so sorry. Oh,
Yeah.
simultaneously, got it. So if you haven't been receiving my emails, I just wanted to communicate a few kind of key things. First and most importantly, the party tonight is not at this hotel. It's just across the street at the St. Gregory Hotel. I think the address is 2200 M Street. Literally a 2-minute walk. If you walk more than 2 minutes, you've gone too far. So Blue Sky, thank you so much for sponsoring this party. It should be a great time. They do have power. They also have a ton of drinks, so the most important part. So that's where we'll be tonight from 6:30 at the end of this keynote on till 9:30. Don't invite your friends. It requires a badge, so no shutting down this hotel. A couple of other things. So tomorrow, of course, we have General Nakasone as our keynote speaker. I'll be sending an email with the contact information to start sending questions in. We'll be accepting questions from this evening all the way up and through the General's keynote tomorrow. And so you can just kind of submit those in advance. And I think the last kind of key thing that we have some information on, but not a ton, is the hotel check-in situation. So if you're staying at this hotel, I believe they're no longer accepting guests. There are 2 links that got sent out in an email that provide different hotel information, as well as discount codes and refund information. Best to speak to the hotel directly, but if you have an issue, do find one of the organizers and we're happy to talk about it and talk through that. So again, if you have any questions, find one of us. I probably should have ended with a party. I feel like that was more of the upper. So yeah, please join us for drinks. Regarding the Blue Sky party, the Hacker Disco, in your swag bag you should have drink tickets. They're little admit one, red tickets. If you didn't get some in your swag bag, you can also find an organizer, or you can find Blue Sky Innovators, who has a roll of tickets to give at their discretion. So, okay, great. I'll end with the drink stuff. And now Winona, thank you.
Journey. Thank you all so much again for dealing with us, and as the power has continued to be a little bit of a snafu. But I'm so honored to introduce a man who does not need introduction to give our closing keynote on memory safety. Halvar Flake is a security researcher and entrepreneur well known for his contributions to the theory and practice of vulnerability development and software reverse engineering. And yeah, I guess we'll have you take it away, Halvar.
Well, good evening, everybody. My name is Halvar. I was just introduced, so I guess I can start with the talk. I'm still trying to get to grips with the power situation, but it's quite the adventure. The screen is locked now, so.
That's why I stopped.
I thought you were being inspiring.
Right, so the talk is titled, Is this memory safety here in the room with us? And the talk is about where are we at with regards to memory safety and what is this memory safety in the first place, because it's getting a lot of play in various circles and it's clearly an important concept, but it's also sometimes a little bit hard to pin down exactly. So let's get started. The first question is, why would we want something like memory safety in the first place? And I'll take a very, very zoomed out, abstract, high-level view of why memory safety is a useful thing. And this view, we have a concrete computer, like a CPU, that we want to run some stuff on, or we want to do something. But the something that we wanted to do is actually a sort of finite state machine that we would like to have. So we've got this very complicated, very powerful device that has an extremely large number of states. And really we want something that has many fewer states. And we write software to emulate this thing that we want to have that has many fewer states than the machine can have on this very complicated, very powerful device. So we design a machine that we want to have, which we usually call our software, and then we implement it, and yeah, we try to run the software that we would like to have on the machine that we have. And this FSM has a bunch of states that we have intended it to have, which we call sane states, where everything is going peachy, the software is doing what we want it to do. And then something bad happens, a bit flips in DRAM because of manufacturing, or somebody writes outside of bounds somewhere, a variable gets assigned a value it shouldn't have in our minds, and we enter a state that isn't part of the original design, a so-called weird state, a nonsensical state, a state that really shouldn't be there if we had our way and hadn't, like something unforeseen hadn't happened. And then we still get to apply, as an attacker, transitions on this state. And these transitions are essentially functions that take a state and they spit out a state. But now we're feeding them with states that shouldn't be there in the first place. So we get one weird state, we apply a transition that is designed to go from a sane state to another sane state. It's now applied on a weird state, and we get to another broken state, and so forth. So we've got this machine, somebody shakes the machine really badly, it goes into a state where it shouldn't be, and then we keep on interacting with this machine, which is now in a state that it should have never entered in the first place. And we keep on driving this machine through these states where it shouldn't be, to a place where it shouldn't go. And that's what we do as attackers, that's pretty much our day job. And eventually we drive this machine to somewhere where security properties are violated. And in practice, this is not a trivial violation normally. Like we're looking for something where the machine does something that is really outside of the bounds of the imagination of the person writing the software. In some sense, like a car thief does not expect the car that they're breaking into to grow wings and start flying. But largely, when you take over a machine, this is what you're doing. You're really transforming what the thing does, largely by unlocking power that is latently there, but is just barely constrained by the software. So, in real-world machines, you've got this nested set of states. I have another picture that I didn't put on the slides, which is essentially a Mozartkugel, like an Austrian confectionery. If you cut it open, it looks roughly like this diagram. And you've got sane states, the states that the software should be, or the machine should be in. And then you've got the documented states that the machine can be in theory. And then you've got, of course, more states where like real physics start playing a role. For us, we really only care about the innermost two circles for now. And what the attacker does is, you've got the sane states inside of the green. Somebody knocks the machine, you enter a state that's somewhere in the red, and then you forge a path through the red until you reach somewhere where you want to go. And memory safety really tries to draw an extra wall into this diagram, which at least, while it can't guarantee that you're always in an intended state, it at least tries to verify certain invariants about the reachable states in the machine. So really, memory safety tries to draw an extra wall into this diagram so that things don't go to haywire. And the way I try to describe this, well, I'll describe this later. Oh, you know, there's a slide missing? No. Oh, good. We'll come later. Really when you're programming, you have the machine which has a lot of different states that you can reach, and your different programming languages to some extent allow you to reach different subsets of the state space. So if you have just a small finite state machine, let's say a very simple UI app that you can run on the thing, there's very few states on the machine that you can reach. They're very constrained by this original application. If you've got a regex engine that allows you to input arbitrary regex, so you can reach larger state space. And then you've got languages like Java and Go, and you've got Save Rust, and then you've got C, C++, and Unsave Rust, and they allow you to reach bigger and bigger subsets of the state space the machine can have, and finally you've got essentially raw bytes where you can end up doing whatever the machine is capable of. It's important to keep this in mind that, in essence, the programming languages try to restrict the number of states to some extent as well, particularly when it comes to things like garbage collection and so forth. So, what does memory safety provide? In C and C++, pointers and array indices are exchangeable, but also very special in a very particular way. Corrupting a pointer or an array index and writing after it, or writing to a pointer after the memory has been released, essentially throws everything you can say about the state of the overall system out of the window very quickly. Like I like to describe this as you're letting the unicorns escape. Right? So you're just barely containing the unicorns in your machine, and then once you dereference or once you write to a pointer that is no longer valid, really anything can happen. Rainbows, unicorns, wings sprouting on a horse. Things go really, really crazy. So the reason why this happens is that a pointer that has gone out of bounds can point to pretty much anything. Like you really don't quite know what will appear underneath a pointer that has gone out of bounds or that has gone out of validity. And then writing to it breaks the relationship between the source code of what you're running and the state of the machine almost entirely. Like once you've done so, it's very, very difficult to make any sane reasoning about the states of the machine from the source code. And it turns out that pointers and array indices are special this way because normal business logic variables do not behave like this. Like the cascading effect of one of them being wrong is not nearly as disastrous. Usually you can still reason pretty well about what might happen if you're just corrupting business logic. So what does memory safety provide? If you're providing memory safety, you keep the abstract machine that your original language designed largely intact, which means in this diagram that we have where the different languages can reach different sets of states, you're still constrained to the states that the language allowed you to reach. You're not doing something particularly insane. So in some sense, a link between the syntax of your language and the source code and the behavior of the machine is maintained. A horse largely stays a horse. It doesn't grow horns or wings or anything like it. The software stays on some level of tracks, even though it may be buggy, even though it may move too much money around and so forth. It doesn't do arbitrary stuff. As an example, very, very naive example, but let's say you take a memory safe input program and you just draw a graph with edges where on the left-hand side you've got a type that is being assigned to, on the right-hand side you've got the type that you're assigning from, usually contained in an encapsulating data structure. That graph will stay largely valid no matter how buggy the program is, as long as you don't corrupt pointers or array indices. So you can still have some amount of reasoning of what's happening just from the source code. Okay, so how do we achieve memory safety in reality? It's usually, there's many, many components to it, and there's many competing definitions of memory safety. I guess a good, one of the definitions of memory safety is no matter what you do, the language will stay in defined behavior. Not sure whether it's a perfect definition. In practice, the two things people care about are spatial safety, which means you can't go out of bounds with your array dereferences, and temporal memory safety, which means you can't dereference a pointer after the memory underneath it has been released and reused. And in theory, you can prove the absence of, improve these properties, this program is spatially safe and temporally safe. For arbitrary C and C++ programs, if you had a sufficiently powerful static analyzer and proof checker, but in reality this isn't done, so you have to modify your, well, in reality it's not feasible yet. So you modify your languages and sometimes your hardware to have safety mechanisms that allow you to have spatial and temporal memory safety. They're usually implemented either in runtime or in compile time or in a combination thereof. And we have to remember that application logic can still become arbitrarily confused, but the goal is to avoid such confusion to ever corrupt pointers or array indices which are equivalent to a pointer. Okay, so in practice we obtain spatial safety by doing runtime array checking. And you do that by moving all your array accesses in your language to a centralized short point, like an array class or something like it. You have to remove pointer arithmetic, because you need to have everything go through that short point. And if you do need pointer arithmetic for your software, the assumption is usually that the only reason you need it is because you need a subset, like a continuous subset of an existing array. So you introduce something like a span class or a slice in Go, which allows you to do the things that you usually want to do with pointer arithmetic in a safe manner while still providing the language with the unique short point at which they can check dereferences. You also try to remove direct array indexing from the language by having more iterate over every element of the container style loops than loops with an explicit index that you need to check. This is a combination of compile time and runtime measures. And then we get to the more difficult problem, which is temporal safety. And the thing really is there's a variety of different techniques for obtaining temporal safety, all with their pros and cons. The most popular one is garbage collection. You just remove the ability for people to manage memory manually, and you have an algorithm that runs in the background to collect memory and free it again. There's reference counting, where you just count how often people are keeping a reference to a piece of memory. And then Rust really innovated when it comes to production-ready languages by bringing a whole bunch of research from the more esoteric academic proposals into practical use. What they do is they enforce strict ownership where a memory area has to have exactly one owner. And you also have essentially one owner that can mutate things in that memory, or you have multiple references to it that can only read. That's the mutual exclusivity between having multiple references and that can modify, meaning only having one reference that can modify, or having multiple readers, also excludes dangling pointers, because if you only have one reference that can modify, clearly you can't have a second one still referencing to it. Anyhow, so we end up with this list of different flavors of memory safety. There's 5 of them, and I'll just go through the 5 flavors. There's actually more, but for simplicity's sake, the 5 major ones will be discussed here. The first one is, you see the unicorn in a cage made out of a hopefully complete lattice. So we're doing proof checking on software. So in essence, there's an approach usually done in avionics for mission critical systems that are very, very simple. You literally write C, C++ code, usually C code, a subset of C code without dynamic memory allocations, and you co-design your source code with a proof checker on the side, so you can prove absence of runtime errors and fairly strict bounds on latency and so forth for your software. That's really not done very often. Like Airbus has done it for their fly-by-wire system, it's done in some avionics systems, but it's not really something that you do on the consumer side very much, because the cost for developing such code base is quite expensive. And usually, or at least in the Airbus case, they pretty much designed the static analyzer over a period of years while they were writing the software, so they could always extend the static analyzer to check their software. So it was an expensive endeavor, but it is possible. So the benefits of this approach is you prove all your safety properties at compile time, or prior to compile time. which means in the end you're not paying extra performance while you're running for any runtime checking, and you're provable. And you need relatively few assumptions about the correct implementation of your runtime, because your runtime is relatively thin. The downsides, it's extremely expensive. You can't really do dynamic memory allocation. A lot of the things that we do in regular real-world software is just not doable. Okay, second two, garbage collection. So garbage collection is arguably the most popular way of keeping the unicorns at bay. You largely restrict or abolish the use of pointers for array indexing. In Java, you went full reference semantics. Go has reference semantics for pointers and introduces slices for pointers to arrays. You do the array indexing through a central short point, and you remove you obtain temporal safety by removing the ability to manually release memory. And you run an algorithm in the background to traverse the entire heap graph and then determine whether memory can be released or not. It's an old concept from the 1960s, originally for Lisp. We can argue that we know how to write memory-safe software since the 60s. We could have written most of the internet in Lisp. Realistically, garbage collection has been a big success story. Like almost all modern languages implement garbage collection in some sense. And until the emergence of Rust, memory safe was essentially synonymous with garbage collected. But there's no free lunch. And one thing to keep in mind is the most important wall that everybody should know about is the memory wall. Memory wall is the gap between the speed up your processor has experienced and your memory latency over the years. So back when Java was designed, you could access memory at the cost of like 2 or 3 cycles. So traversing a very large graph on the heap was something that seemed reasonable to do. Today, a DRAM dereference is somewhere on the order of 100 to 120 other instructions you could be doing at the time. So traversing a very large graph on the heap is an insanely expensive endeavor. In some sense, the hardware evolution has moved against garbage collection over the years. Meaning the hardware, by virtue of the memory gap growing, has gotten less and less friendly to garbage collection. So the issue really is that temporal safety is difficult because the liveness of an object is a global property of a program, but everybody that builds the program, from the compiler to the person editing the software to the garbage collector, usually only has a local view. So you need, in order to do garbage collection, you need to do a full traversal of the entire heap graph. And that's in modern systems that like data locality, that dislike accessing DRAM, it's a pessimal workload. Like everybody, when you start learning programming in, let's say, C++ these days, people tell you never use stdlist, just don't use linked lists at all. Because chasing long chains of pointers is the worst case workload for a modern machine. And a garbage collector, by definition, does this. So you pay quite heavy cost in many ways. You pay the cost for traversing the heap graph. You pay the cost for polluting all your cache lines because you can't reuse memory quickly enough. Imagine you have a loop in which you're allocating small objects that you can let go at the end of every loop iteration. So in a non-garbage collected language, you're using the objects, you're releasing them, you're reusing them because your allocator will hand them back to you. In a garbage collected language, you're going to pile them up on the side and then garbage collect them and then reuse them. Which means instead of reusing the same physical memory addresses, which are then very cache friendly, with trashing the cache all the time. And you're consuming much more memory, and that translates to both dollar, in terms of costing you more DRAM to buy, but also more power consumption in practice. There's a beautiful paper in 2005 where somebody tried to quantify like how much am I paying for garbage collection. It's a great paper, everybody should read it. And honestly, if we were in such a bizarre situation, I would encourage people to just fund a grad student to rerun it on modern garbage collectors. But the paper essentially establishes that you can get cycle equivalent performance from a garbage collector, provided you give the machine 5 times as much RAM. And if you only give it twice as much RAM as manual memory management, you're going to pay up to 50% more cycles. Now, this might have gotten slightly better because garbage collection algorithms have improved, or it might have gotten worse, nobody knows. But the reality is you're paying much more in DRAM if you're running a garbage collector language, if you want to have similar performance to run garbage collection. And the napkin math for this is actually quite dire, because on a modern system, you're going to draw, like this is not a GPU system, this is a regular server, you're drawing 25 to 30% of the power budget into DRAM. So if you're now 5xing or 3xing your DRAM requirements, you'll probably double your power consumption of the thing. And we all know that modern data centers tend to be power constrained. The global data center power usage per year is about 100 billion. So if you have a significant impact on that, you're very quickly speaking tens of billions of dollars just in power consumption per year. So, well, I'll skip this slide because it's not that interesting. So we have another flavor, reference counting and runtime array checking. So you obtain spatial safety by runtime bounds checking, and you obtain temporal safety by reference counting. And if you look at the design of the Swift language, Swift famously, at a time where garbage collection was all the rage, instead of doing a garbage collecting language, they opted for reference counting. And this is part of Apple's obsession with battery lifetime. Right? Because if you look at Apple devices, Apple places a premium on having good battery life. For example, when Rowhammer came out, iPhones were largely immune because they all had ECC in there, not for security reasons, but because you can reduce the amount of refreshing you do for your DRAM if the DRAM can correct errors. So Apple has always been very good at doing a top-to-bottom engineering that maximizes battery life and minimizes power draw. So when they designed Swift, they also decided reference counting is a good thing, because if you have a phone in your pocket, most of the time the CPU will be off. So the DRAM refresh, keeping a DRAM alive, is a much larger component of your overall battery life than in other scenarios, in server scenarios. So they didn't want to pay 2x more DRAM power draw. So you get temporal safety without a garbage collector, and you're essentially as good as a bad manual memory manager that is nonetheless correct, meaning the moment that the last reference goes away, you drop the memory and it's fine. Keeps memory overhead low. You don't pay the power to keep your garbage alive, which you do in a garbage collector. The big downside is that on multi-core systems, reference counting, depending on the level of granularity, can become very, very expensive. Just imagine you have a long list. Let's say we have a linked list that we need to traverse, and every individual component of the linked list needs to be reference counted in my language. Out of a sudden, I turn a fast read-only iteration of the list into a series of synchronized read-write operations, which tank my performance pretty drastically. So I need to be pretty careful with how I design my data structure and what level of granularity I introduce the ref count. Which means this is also not the true one and only solution. So the next flavor is the strict ownership semantics that Rust provides, and again, runtime array checking. We see the Rust crab containing the sad unicorn. Rust's big contribution really was to kill the notion that you need to be garbage collected in order to be memory safe. And through that, the discussion, can we have memory safety in performance critical systems? Like we couldn't have had that discussion previously, because we didn't really have a production-grade programming language that has memory safety guarantees, that doesn't have all the problems of a garbage collector. And the idea is, like, there's a number of design choices in the Rust language that are very clever. You have this exclusivity, either one mutable reference or multiple immutable ones, and that removes use after freeze. It also removes the possibility of mutating data structures while you're iterating over them. Iterated invalidation is a very common problem in C++ code bases. For better or worse, meaning you can't do this anymore, which can have performance impacts because sometimes you want to simultaneously iterate over something and update it at the same time. There's some cost to do this, because Rust code requires you to do lifetime annotations sometimes. In general, when you're deriving a reference to something from other references, you need to tell the software that the lifetime of this reference depends on the lifetime of the original objects you derive this from. Long story short, Rust has been somewhat of a game changer. We have the possibility to have memory save programs without a garbage collector, and with all the drawbacks, without all the drawbacks of the garbage collector. And Rust got a lot of things right. So you have a type system that allows you to prove temporal safety at compile time. You introduce the runtime checks to get spatial safety, and Rust tries more than other languages perhaps to avoid indirect dispatch, which means the compiler can reason better about the resulting binary, which means the compiler can omit more of the bounce checks, absorbing some of the runtime cost of bounce checking all the time. It has a bit of a learning curve. I think everybody that starts with Rust has a bit of a traumatic first contact with the borrow checker. Unless you're already a very, you've either been through a sort of boot camp where somebody that beat proper C++ behavior into you, or the borrow checker will do it. It has the interesting side effect that even if you don't write Rust habitually, you usually become a better software engineer by writing Rust for a while, because the borrow checker will beat some discipline into you. It's gained a lot of industry traction in domains that were previously reserved for C and C++. AWS is a big fan, parts of Android. Microsoft is surprisingly Rust-friendly. And we have Rust in the Linux kernel in some way, shape, or form. And there's people like Oxide Computers that are building pretty low-level firmware in Rust. And when Mozilla was still a financially more healthy organization, they even started an effort of rewriting an entire browser engine and a JavaScript engine in Rust. With Mozilla running out of funds, those efforts have stalled. They're still alive, for some definition of alive. Well, we don't currently have a browser in Rust. There's a bunch of pros and cons of the strict ownership structure. The big pros are you release your memory pretty timely. You essentially get similar, you don't get garbage piling up on the side. You have relatively little runtime overhead because you're doing all this at compile time. You can have data structures that you can iterate over rapidly without having to do reference counting on every one of them. And Rust implements reference counting primitives, so you can choose the level of granularity to do reference counting at if you choose to do reference counting. You can still write unsafe code, but you have to enclose it in unsafe blocks. So a lot of the things that you want to do when you do systems programming are still available as an escape hatch. The downsides are the heap structure is enforced from above, which kind of limits your design space at times. Directed cyclic graphs and RCU-like high-performance structures are possible to do in unsafe Rust, but essentially impossible to do in safe Rust. And you have a pretty steep learning curve for people facing the borrow checker for the first time. So Rust forces very specific architectural choices on the programmer, and they're almost always, but not always, the right choices for the task. So, yeah. Then we have flavor number 5. The reason why we have clouds on this is because it's largely vaporware at this moment. And that's the attempt of retrofitting memory safety into C++. And it's a bit of both a sad and happy story. We have a lot of C and C++ everywhere. The reality is just that this world is built largely on C and C++. And ideally, we don't want to rewrite all that software because it's a lot of software, it's a lot of money that we've spent on this. So, Bjarne Stroustrup, like a week ago, published an article called 21st Century C++, in which he lays out a roadmap for getting memory safety and resource safety to C++. And it's essentially extra annotations to enforce language rules per translation unit, so you can enforce types and boundaries and lifetime constraints, and the ability to disable them for individual lines. And it all looks very good on paper, because it would allow backward compatibility and incremental porting of existing C++ code bases into memory safety. The real downer is it's really an approach on paper, and the C++ security profiles working group has been working on this since 2015. And we don't have an actual memory safe prototype to do this in C++ now, so it's been essentially 10 years of not getting there. And Sean Baxter, who worked on this for a long time, wrote he's one of the Circle language folks, he wrote a very detailed and very good article last fall about his criticism of the C++ safety profile approach and why he thinks it cannot work given the constraints the C++ community has set themselves. So, there's not much more to say. I should mention there's various hardware approaches, memory tagging and Cherry. I'll be very quick about them. Memory tagging essentially adds a couple of bits of extra metadata into every pointer, and then whenever you dereference the pointer, it ensures that these metadata bits match the underlying memory allocations, metadata bits. It is implemented in some ARM cores these days as a relatively good mechanism. It's a reasonably good way of retrofitting some semblance of memory safety into existing C++ code bases. Comes at a certain DRAM cost because you need to store the metadata bits somewhere. I will not go too much into it. Likewise for Cherry, I'll skip over this because while we have real silicon implementing this, I don't think it'll hit any device that we care about anytime soon. I should mention the Miracle Pointer as well, but I'll just go over this because it's already turning into a bit of a slog. Like memory safety is a topic with many nuances, and everybody has some idea on how to improve it. So the things that we have learned already about, like from essentially the Rust experience, is that the big wins are when we manage to turn problems that are normally only solvable by whole program analysis into problems that can be locally solved by the compiler. And the global nature of determining liveness is one such thing. You get problems when you mismanage it, so you get memory corruption, or it becomes very costly when you try to do it in an automated manner, garbage collection. And then Rust's idea of using a much more powerful type system to turn the global problem of liveness into a locally checkable problem that the compiler can check on compilation time seems to work. Right? If you can turn any problem that you have into something where the compiler can reason about one function at a time and then compose everything into a working thing, it works. And what's funny is, if you squint, proving local properties for each function and then composing the local proofs into a whole program proof of safety with the use of copious annotations in the form of type specifications, you end up doing almost the same thing that they do in the avionics case, right? Because you're co-developing your software with the type system that beats discipline into you all the time. It's very similar to writing C code and have a theorem prover try to prove stuff all the time. So in the limit, the approach of verification of the avionics systems by whole program analysis and the approach of strengthening your type system and turning more and more of the type system checking on compile time into a theorem prover approaches the problem. It's essentially the same. If you squint enough, it becomes the same approach. And Rust is already adding a Prolog-style theorem prover into the compiler to deal with implications inside the type system. So we're already converging to something similar there. Anyhow, all of these approaches are not free. You can pay a lot of DRAM overhead when doing GC, or you can pay the architectural restrictions and excluding certain high performance constructs when you're doing Rust. But you can't have all your performance for free while getting memory safety. Which shouldn't be surprising, right? Because you're restricting yourself. So where does this all leave us? One thing that we should note is writing a memory-safe user-space network application like an SMTP server or something like this is a solved problem. We can do this now. In some sense, we could have done this in 1960 or 1994, but it's certainly a solved problem now, and perhaps we should do more of it. So I mean, we have to pay the cost for runtime overhead, we have to exclude the possibility of runtime bugs, and so forth, but in theory we can write some safe software. Interestingly though, we don't really have a safe web browser yet, we don't have a safe JavaScript engine yet, and a surprising number of real-world kernel drivers would still allow privilege escalations in spite of being memory safe, because the things that generate kernel bugs do not necessarily mean they have to be memory unsafety issues in the classical sense. So what is not yet covered well by the existing memory safety mechanisms? The first thing is writing safe, unsafe Rust is not easy. If you try to write anything in Rust, you'll very quickly find a bunch of so-called unsafe blocks. And then knowing that these unsafe blocks are safe is actually pretty difficult. There's a book called online book called the Rustonomicon, which is the reference for writing safe, unsafe Rust. And it has a big warning when you just load it saying, okay, this is possibly all outdated. Please also check the issue tracker. So this is very much work in progress. And there is no authoritative, complete source on how to write safe, unsafe Rust. It's very, very easy to write unsafe Rust. Because you not only have to understand memory allocations and so forth, you also have to understand the intricacies of the type system pretty well. A common mistake, for example, is when people write new data containers in Rust, they make the data container shareable between threads, which normally you need to do that explicitly, but then don't annotate the types to ensure that the contain type is also shareable. So in essence, you have like a shareable container of something, and you put something non-shareable inside then as a programmer, and boom, you've got memory unsafety, because some library writer that wrote the container didn't annotate the types properly for the compiler to tell you you can't do this. So you think you're writing safe code and you're writing unsafe code. Then something that the Rust type system has no handle on, which is actually reasonably important, is shared memory time of check, time of use. We know this when like a device driver in Linux or in Windows reads from user space multiple times. So you write some code and you check a variable, and then you read the variable again, and now it has a different value because somebody in user space changed the value of the variable. And the type systems that we have right now don't really encode the property yet that you can only read this value once. Like, you can never access the same memory twice because then it might have changed. This happens on the user space kernel space boundary, but it happens essentially wherever you have shared memory accessible from two domains where you can't trust the other domain. So maybe things like my baseband has been compromised and the baseband communicates with my host CPU through shared memory. My NIC has been compromised, the NIC communicates with my host through shared memory, and so forth. Another pattern, bug pattern that was very common in C++ that also the type approach at the moment doesn't solve. In many browsers you had a situation where you had some C++ code, the C++ code took a reference on another object, did some checking of that object, and then more or less accidentally caused a callback into JavaScript. And then that object was mutated from JavaScript, so the check was changed, or the check value was mutated, or the memory was deallocated. And it's very similar if you squint to these time of check, time of use bugs that I just mentioned. The issue really is when you cross language boundaries in that manner, you need to make sure that whatever other language gets control in the meantime respects your type guarantees. And that's a bit of an unsolved problem. You can fill an entire book with the intricacies of FFI in memory-safe languages when you have to interface with non-memory safe subsystems. Go has very convenient interop with C code using CGO. There are many very dangerous footguns there where you need to make sure that the memory, like you're not passing pointers to objects that live on the Go heap to any C code, because in theory the garbage collector can move memory around. And Rust has other issues. One I found particularly hilarious today was Rust didn't really support, I'm not sure whether it does now, but historically it didn't support dynamic linking very well. And there was a situation where somebody had written essentially some Rust code to do dynamic linking and calling from one library into the other. And they had a B-tree map, and that was used in both libraries, except that the B-tree map implementation had a static variable as a root node for every tree. And now they ended up having, like the one library had one static variable here, the other library had a static variable here, and they passed the pointer from this library into that library, and that library then freed that B-tree map, comparing whether the root of the tree was equal to its own root and freeing all other nodes. Because the tree came from here, it just ended up freeing all the nodes, including the static variable over here, and you had a memory corruption. There are issues when you interact with multiple libraries. Another thing that happens is when you have, like in the rare case that you really need to have a directed cyclical graph, there's only two ways of doing it in Rust, and that is using array indices into a pool of nodes. But then you're using array indices essentially as pointers, right? Because you have to keep track of lifetime again, because you don't know whether that thing is still alive or not. Or you use reference counted or multi-thread reference counting wrappers. But then you need to be very, very careful about not doing cyclical references and leaking memory. And both have the disadvantages. And in practice, you end up a lot of times with the proto-pointers, array indices as kind of pointers hack. And then you get use after freeze in spite of the fact that your memory is safe. And there's still some type safety enforced. But it's very strange because at that point, you are kind of memory safe, but also kind of not. So it's just a weird place to be. I mean, JIT miscompiles almost all the browser bugs we've seen in recent years were not issues of memory safety, there were issues of the compiler that generated the code being mistaken by some optimization. So the problem of having to emit fast code rapidly from an adversarial source is a problem where many bugs will live no matter how clever your type system is. You've got all the hardware errata, when you can get the hardware to misbehave, your memory safe language won't catch you. Rawhammer, there's a hilarious thread on the Mozilla dev forums from 8 years ago where AMD's Bobcat laptop CPUs had an erratum that the Mozilla guys kept hitting with their JIT. And they try to debug all these strange crashes they're getting, only from the symptom of getting execution traces that cannot happen. Issues like leaking memory through SIMD registers in the CPU. There's a paper called Cores That Don't Count that points out that at sufficient scale, you get defective CPUs that are silently defective and silently probabilistically defective. Now, this isn't very useful for targeting one particular target, but it's reasonably useful if you're attacking a cloud provider, because you can just ask for a new machine repeatedly until you get a machine that has the desired insanity. So, there's a lot of weirdness that we don't know how to deal with very well when it comes to shared memory communication between devices. The CPU in modern systems is more and more becoming the bottleneck. The systems that we're looking at are more and more mutating to a sort of network of systems that all communicate via shared memory. At the moment, the CPU still sits in the middle, so you have CPU and GPU communication via DMA, you have CPU and NIC communication via DMA, but no direct communication yet. But my prediction is, because it's so difficult to shovel all the machine learning training data from the network into your GPU, you'll get direct shared memory between NIC and GPU pretty soon. And also between storage and GPU. So you'll have almost a mesh of devices that communicate with shared memory. And I don't think we're very sophisticated at writing programs to do that yet. And driver logic for managing shared memory is prone to logic bugs. There's a link here. Mali GPU, mobile, some driver bug that allows you to map memory in a way that you shouldn't be mapping it. There's no memory safety or undefined behavior bug to be seen. It's really just the logic is convoluted and then wrong. And also issues like, are the various devices in my device respecting my operating system security abstractions? Like, Can two processes read each other's GPU memory? Can two processes access shared memory otherwise that shouldn't be shared? Okay, what's next? What's coming in the future? I mean, it's difficult to ignore LLMs as much as I try. And it has to be said that LLMs as driver for theory improvers are improving rapidly. And that opens up a number of interesting opportunities. If you look at efforts to validate unsafe Rust formally at the moment, it's mostly done via a framework called Iris, and then that generates proofs for Coq. And helping an LLM drive a theory improver that verifies that unsafe Rust is safe. So you can actually build a program in safe Rust, and then have all the unsafe blocks that you've pulled in via libraries validated for being safe, unsafe Rust. That would give you a lot of confidence that the overall software in the end is safe. And the other area which is kind of interesting is, if you read the criticism of the CircleLang guy for the C++ security profiles effort, one of the things he's arguing is we won't be able to retrofit memory safety into C++ without heavy annotation. But that sort of annotation might be partially automatable by LLMs. And the other question is, as LLMs, as drivers for theory improvers improve, will this lower the cost of verifying systems? Because right now, the main reason we can't do a lot of verification is it's expensive as hell. So the question is, will it become cheaper so we can do more of it? There's lots of research and engineering that you need to do, or everybody needs to do. We kind of know how to build a safe user space application now, but almost nothing in our infrastructure is memory safe right now. We don't have a memory safe mainstream OS kernel, we don't have memory safe basebands, we don't even have a memory safe FFmpeg, we don't have a broadly deployed memory safe browser engine, we don't have a JavaScript JIT that's memory safe, we don't even know how to get there. Pretty much all high-performance networking libraries that do kernel bypass are unsafe. Outside of Oxide, very few people write firmware in Rust. Even Rust in the Linux kernel is struggling if anybody's following the politics here. Very few Rust crates are verified. We have no viable path to convert legacy C++ to memory safety. So we've kind of figured out how to do one thing, but there's a metric ton of work ahead if we want to do more of it. Another thing to remember is the language of the future will be neither Rust nor C++. At least not today's Rust or today's C++. It's pretty clear that long term we're going to evolve languages into having more powerful type systems that allow us to make more statements at compile time. Especially because theory improving as part of the compiler chain will become more sophisticated. There's a secondary part to it. A very stringent type system is a form of correctness oracle. And if you look at what sort of progress there's been in AI recently, a lot of it depends on having a verification oracle and doing reinforcement learning on it. So a stricter type system, to some extent, will allow AIs to learn more about writing correct code, which will then lead to the AIs improving faster on this stricter type system, which is going to be an interesting dynamic. But until then, the unicorns can roam. And remember that with sufficient memory corruption, anything is possible. Thank you. I had hoped to escape the questions. No, all good, all good. Any questions? Yes.
So I don't know much about Go, but back when you were talking about garbage collection and the second thing when you showed the garbage can unicorns, you were talking about the spatial safety and then you were talking about temporal safety.
Yep.
And you seem to be implying that Go would gain temporal safety, but I was under the impression that it didn't have temporal safety.
So Go has temporal safety by virtue of having a garbage collector. It doesn't necessarily have multi-threading safety. Well, so if you stick to Go's paradigm for sharing data, then you have it. But you don't have to stick to it. So it's a bit like unsafe Rust in the sense that Go allows you to do something unsafe, but it does provide you with mechanisms to do something safe. So as long as you use Go's channels for sharing data between threads, for sending data between threads, then you're safe. The moment you share mutable state, you're not safe. All right. Thank you.
Alright gang, we are moving to the party. Two very exciting developments. There will be temporary tattoos there, and in order to fundraise for additional generators, I have this limited edition swag that I was going to give the organizers as a present, but instead we've decided to fundraise for our generators and our additional lamps for tomorrow instead, just in case, 50-50 chance if we have power. It's based off of our junkyard mascot. She's a cute little computer monitor plushie. In order to make sure that we can generate the funds to do so, because we only have 20 of these that we're selling. It's a minimum donation of $130, which I know is expensive, but so are our backup generators that we had to go source from REI today. If you see somebody with one of these, they are for sale, and otherwise we'll see you at the party tonight. Thanks all.